Okay, this is lesson 5.5, trigonometric identities. A trig identity is a mathematical equation that's always true regardless of the values of a given variable. If the identity is rational, the denominator cannot be zero and restrictions on the variable must be stated. We're going to develop a couple identities using a practice called XYR substitution. And then once we've developed or proved these identities, we're going to use these identities to prove other identities. So this XYR substitution is something we can do to develop a bag of tricks, basically, a bag of identities, a toolkit that we can use to prove other identities. And we already have a couple identities that we have not proven but used in the past. And those are the reciprocal trig ratios, or the secondary trig ratios. The fact that cosecant is 1 over sine. That's an identity. That's the definition of the secondary trig ratios, and we use those identities to prove other identities. So here's 3 more we're going to develop today. We're going to develop that tan theta is equal to sine theta over cos theta. Cotan theta is equal to cos theta over sine theta, and one called the Pythagorean identity that says that sine squared x plus cos squared x equals 1. So let's give it a shot here. To set up a proof for an identity, we're going to use a format called a left side, right side. And this is a format for proving an identity that we're definitely going to take advantage of in high school. We break our identity up into a left side and a right side. So we're going to say left side, and what's on the left side? Well, tan theta is on the left side, and on the right side we have sine theta over cos theta. And we're going to prove this identity by changing one of these sides to look like the other. And the side we're going to change is the sine over cos. We're going to turn that into tan. And the way we're going to turn it into tan is we're going to use x, y, and r to represent opposite, adjacent, and hypotenuse. And if you don't remember which one's which, well, I'm going to draw you a nice little triangle here. If we had a triangle on the Cartesian plane representing an angle from standard position, the x would be the horizontal, the y would be the vertical, and the r would be the hypotenuse. So if we're talking about sine theta would be opposite y over hypotenuse r. And cos theta would be adjacent x over hypotenuse r. And tan theta would be opposite y over adjacent x. So we're going to use these equations and substitute in for sine and cos. So sine is y over r. I'm writing my fractions sideways to kind of save some space here. Cos is x over r. So now we have y over r divided by x over r. How do you divide a fraction? Well, you flip the denominator and multiply. So we've got y over r times r over x. And what happens if we multiply? I'll write it out. We get y r over r x. And we have an r on top and bottom. We can divide them away. R divided by r is 1, so we're just left with y over x. And y over x, if we go look at our definitions of sine, cos, and tan, y over x is tan. So my last step is to say that this equals tan theta. So what I've done is I've taken my right side, sine over cos, and I've turned it into tan theta using x, y, and r substitution. Once we've done this, we can say left side equals right side. And B. B says cotan theta equals cos over sine theta. And I'm going to leave this one to you to try on your own. You're going to set it up as a left side, right side, and you're going to do a XYR substitution for cos and sine and see if you can turn it into cotan theta. You can pause the video, try it now, or you can keep continuing with the video and come back and try it after. We're going to move on to the Pythagorean identity. Sine squared x plus cos squared x equals 1. So same setup, left side, right side. And right side. Now you might ask, what side should you start working with? Well, if you're doing XYR substitution, you're going to work with the complicated side because there's stuff that you can do. If we replace these with X, Y, and R, there's going to be something there. If we replace 1 with X, Y, and R, there's so many places we could go. We could write Y over Y, we could write X over X, we could write R over R, and it's just too many different combinations to guess and work from. So we're going to turn this into hopefully look like 1. So let's do our XYR substitution. Sine is Y over R. Sine squared X means Y over R squared. And cos squared X means X over R squared. And if we square these, we get Y squared over R squared plus X squared over R squared. Now we have a common denominator. We have R squared on the bottom, so we can write this as one fraction. Y squared plus X squared on top. Now, if we go back and look at our triangle from the beginning, we have an X side, a Y side, and an R side, usually an A, B, C. Now if we use Pythagorean theorem, look what happens. A squared plus B squared equals C squared, or Y squared plus X squared equals R squared. And the reason this is called the Pythagorean identity is because Y squared plus X squared equals R squared. We use Pythagorean theorem to replace the Y squared and the X squared. And now we have R squared divided by R squared. That is 1. So we have proven the identity. We can say left side equals right side. And there's a designation that we can use to show that we've proved our identity. After we write our left side equals right side, we can write QED. QED. And make sure you ask me in class what QED stands for, and I'll fill you in. All right, so X, Y, and R substitution. We don't actually use this to prove identities generally. We're going to use other identities to prove other identities. But we can use X, Y, R to show you why a couple identities that we're going to use over and over and over again work. And at this point, you're never going to use X, Y, and R substitution again unless there's an explicit question that says use X, Y, R substitution. If you get a question that says prove an identity, you're not going to use X, Y, R substitution. And I'm going to show you a couple of those. So here's a little note. Once you've proven an identity, you can use it to prove other identities. Now, I've put these 3 identities on your formula sheet, so you can use those identities for the rest of the course, and you don't have to redevelop them using X, Y, and R substitution. So let's try to prove this identity. Prove the Pythagorean identity 1 plus tan squared theta equals secant squared theta. Well, let's break it down left side, right side. Left side is 1 plus tan squared theta, and right side is secant squared theta. Now, reasonably, you can prove an identity from either side. It's just sometimes one side's easier than the other, and it's usually easier to take something that's more complicated, so in this case 2 terms, and turn it into 1 term. When you only have 1 term, it's kind of hard to break it down because there's so many different avenues you could go down to break down 1 term, and that can become challenging. So my recommendation is when you're choosing a side to work with, choose the more complicated side and try to make it look easier or look simpler 1 term. So let's give it a shot. We got 1 plus tan squared theta. So many places we could go. Well, let's change tan, because one strategy that's fairly effective when trying to prove an identity is if you can take everything that you have and write it in terms of sine or cos, that's like common language for trigonometry. Every identity can be written in terms of sine or cos. Like tan, we know tan is sine over cos. Secant is 1 over cos. Everything can be turned and written into sine or cos. Cotan, as we just showed in, well, maybe you haven't shown it yet, but in B, cotan is cos over sine. Everything's common language is sine and cos. So we're going to use that strategy. Tan is sine over cos. Tan squared would just be sine squared theta over cos squared theta. And how does that help us? Well, right now we have 2 terms. It doesn't really help us. What we can do, though, is when you have 2 terms, one strategy is to create a common denominator and turn it into one big fraction. So we're going to give that a shot. How do you turn these 2 terms into one big fraction? Well, you write 1 as a fraction over cos squared theta. And how we would do that is we would turn 1 into cos squared theta over cos squared theta. Second fraction stays the same. And now we have a common denominator. So we can write cos squared theta plus sine squared theta over cos squared theta. And if you take a look, the Pythagorean identity says sine squared theta plus cos squared theta is 1. So that means cos squared theta plus sine squared theta is 1. One over cos squared theta. And hey, secant is just 1 over cos. So secant squared theta must be 1 over cos squared theta. And now we've proven the identity. We used a couple things here. We used the identity that tan is sine over cos. We created a common denominator, and then we used the Pythagorean identity. We used 2 different identities to prove this identity. And now that we've demonstrated it, we can say left side equals right side. Therefore, QED. Forgot the therefore. I wrote it last time. All right. Let's flip the page over. A couple skills that come in when trying to prove trig identities is factoring and expanding. So sometimes when proving an identity, you have to either expand or factor. And I'm going to show you exactly what I mean here. We're going to simplify these expressions by factoring or expanding. So the first one says 1 plus cos alpha times 1 minus cos alpha. And if you recognize the patterning here, 1 plus something, 1 minus something, and the 2 things, the 1's and the cos's, are the exact same, this is a difference of squares. So when we expand it, we should only end up with 2 terms. So let's give it a shot. 1 times 1 is 1. 1 times negative cos is negative cos. Cos times 1 is cos alpha. And cos alpha times negative cos alpha would be negative cos squared alpha. Now if you look at the middle 2 terms, we got a minus and a plus. Those would add to 0, and we would end up with 1 minus cos squared alpha. And that might look simpler, but also there's something else we can do. If you remember the Pythagorean identity from the first page, sine squared theta plus cos squared theta equals 1, we can rearrange this to make it look like this. How would I do that? Well, I'd move the cos to the other side, and I'd end up with sine squared theta equals 1 minus cos squared theta. This is just a rearranged version of the Pythagorean identity. So we can take this 1 minus cos alpha and turn it into sine squared alpha. And that's the Pythagorean identity. 1 plus cos alpha times 1 minus cos alpha, in fact, is just sine squared alpha, which is pretty neat. Let's try another one. Simplify. Right now we have two terms. This is in some sort of expanded form. There's something common to these two terms, though, and that's cos squared alpha. So in this simplifying, we're going to use a factoring strategy. We're going to common factor. What's common to both terms is cos squared alpha. And watch how this simplifies. Cos squared alpha, bracket. If we factor from the first term, we're left with tan squared alpha. If we factor from the second term, we're left with just 1. Now, on the previous page, we proved a Pythagorean identity. And if you look, that Pythagorean identity was 1 plus tan squared theta equals secant squared theta. And if you look at what we have in our bracket, we have tan squared alpha plus 1, and up here we have tan squared theta plus 1. Those are equivalent expressions. So we can replace what's in the bracket with secant squared theta. Secant squared alpha. And what's secant squared alpha? Well, secant is 1 over cos. So secant squared would be 1 over cos squared. And cos squared alpha times 1 over cos squared alpha, well, that would just be cos squared alpha over cos squared alpha, which is just 1. So we've taken something that looks a little bit more complicated and we've turned it into something much simpler. There's another way that we could have done this too, and it's using the fact that tan is sine over cos, and then multiplying sine over cos by cos. Simplifying, we'd get sine squared theta, or sine squared alpha plus cos squared alpha, and that's the Pythagorean identity, and we could say it also equals 1. But I wanted to show you a common factoring strategy as well. All right, one more. We've got cos 4 theta minus sine 4 theta. We have two terms. Both of those terms can be square rooted. We have a difference of squares. So let's factor a difference of squares. If you remember how to factor a difference of squares, it's the square root of the first term, which would be cos squared theta, going first in the brackets. One bracket gets plus, one bracket gets minus, and then the square root of the last term. And you may see something that looks familiar already. The first bracket, cos squared theta plus sine squared theta, cos squared theta plus sine squared theta, that's the Pythagorean identity. That first bracket is just 1. And the second bracket, cos squared theta minus sine squared theta, well, that can be factored again because it's just a difference of squares. So 1 times the bracket would just leave us with the bracket. And if we factor square root of the first term, goes first, 1 minus, 1 plus, sine theta goes second because it's the square root of sine squared theta, and now we have a fully factored expression. That's a difference of squares. So what do we do in this one? Well, in this one, we use the Pythagorean identity again. We used the Pythagorean identity again, and we used factoring a difference of squares. Why am I showing you all this? Well, the reason I'm showing you this is because these are 3 different strategies that come up fairly often in proving trig identities. Expanding and simplifying usually allows you to use the Pythagorean identity to get something even simpler. Common factoring sometimes allows you to eliminate one of the terms that's left after common factoring using the Pythagorean identity. And factoring a difference of squares sometimes also leads to using the Pythagorean identity. These are three different situations that come up fairly often in proving a trig identity, and they usually result in using the Pythagorean identity after. One more set here. Common denominators and rational expressions. Well, here's two more identities. I'm going to do one and then give you a hint on how to do the other. I'm going to do the first one and I'll give you a hint on how to start 6. And if we don't finish 6, that's okay. We can try it in class. In the first one, we've got a left side and a right side. And the question is, which one do we start with? Well, it's a little tricky. You can start with either side is the answer. But we're going to start with the left side because I'm going to show you a neat strategy. The left side is sine theta over 1 plus cos theta. And the right side, I'm just going to write down over here, 1 minus cos theta over sine theta. Now, we have two terms in the denominator. One strategy when proving a trig identity is to multiply the top and bottom by the conjugate, which would be the same two terms with the opposite sign. And why that is a good strategy is because of what I showed you above. If you multiply two terms that look like the factored form of a difference of squares, you end up getting a difference of squares on the bottom. On the top, I'm just going to write it as if I didn't expand it. Sine theta, 1 minus cos theta. And if I expand these out, well, that's actually what I did all the way up here. I expanded these out and I ended up with 1 minus cos theta. And 1 minus cos theta was sine theta. And I'm going to use that to my advantage here. 1 minus, 1 minus cos squared theta. 1 times 1 is 1. Cos times cos is cos times negative cos is negative cos squared theta. And the 1 times negative cos and the cos times 1, those end up adding to 0. So we end up with just a difference of squares. And on the bottom, that difference of squares, we can use the Pythagorean identity and turn this into sine squared theta. And why does that help us? Well, look at where we're going. We're going to 1 minus cos theta. We have that on the top, 1 minus cos theta. Right now we have an extra sign on the top, and if you look at the bottom, sine theta, sine squared theta, we have an extra sign on the bottom. Well, isn't that convenient? We can divide the signs away. And that leaves us with 1 minus cos theta over sine theta, which is exactly what we're trying to get on the right side. So by multiplying top and bottom by the conjugate, we can turn the bottom into a difference of squares and replace it with a single term, and that allowed us to prove our identity. So now we can say left side equals right side, therefore QED. And for 6, I'm going to get you to give that one a shot. The strategy you're going to use in this one is to create a common denominator. And you know what? Actually, I'm going to do this one really quickly with you right now. We want the left side to turn into 0. Left side. Sine theta over 1 minus cos theta. When you have two fractions on the same side of an identity, the strategy that you should use is to create a common denominator and turn it into one fraction. And then from there, you can usually simplify. So what's our common denominator? Well, we have 1 minus cos here, and we have sine here. So in order for you to have a common denominator, you need both of these denominators. So we're going to multiply the top and bottom of each fraction by the other's denominator. So the first one, we're going to multiply top and bottom by sine. So we would get sine squared theta over 1 minus cos theta sine theta. we've multiplied top and bottom by sine theta. And for our other fraction, we're going to multiply top and bottom by 1 minus cos theta. And there we end up with the same denominator. And on top, we have that same difference of squares that we dealt with over here. So we know that this top is going to turn into 1 minus cos squared theta. And then we can turn that into sine squared theta. So I'm going to save all of the work. And because I know that, I'm going to take that and use it to my advantage. And if you look at what we end up with, difference of squares, we expand it, or sorry, factor difference of squares, we expand it, we end up with the difference of squares, 1 minus cos squared theta. We replace 1 minus cos squared theta with sine squared theta, and we end up with two fractions that are in fact identical. Fraction on the left and fraction on the right are the same, and we're going to subtract, and if we subtract, we get 0. Therefore, QED. There's a pretty good introduction to solving trig identities. We're going to spend a fair bit of time in class solving trig identities, and it's something that's definitely going to come up again in grade 12. But for now, thanks for watching, and I'll see you next time.